Okay, I hope I'm recording. Welcome to the third workshop of this semester, spring 2023. It is season 4. Yay! And this is for circuit construction workshop. So the topic of this workshop will obviously be building circuits. Whether it be just with LEDs, resistors. We're going into digital logic this time around, which hasn't been a thing for like last semester. So just off the top, who here has been to one of our workshops before, whether it be last week or last semester or even 2 semesters ago? Most of you? Awesome. How many of you guys have been to the last circuit construction workshop? Do we have any like alumni? 2? 1, 2? Awesome. So we're going to do it linked a little bit differently this time. I remember last semester I pre-recorded some videos and showed them, which was or was not helpful. And let me tell you this, to be completely honest, last semester was a little bit of a disaster. But this time we're going to go over like things very carefully. We're going to go through each part in the circuit kit and describe what it is, and just making sure that you know what you're doing. And the difference is this time is we're going to have a kind of like live demo where you get to go ahead and follow with the, I'm going to put the camera up here and you get to follow along, you get to build some circuits, and then afterwards you can go to the lab and build your own. There'll be a few challenges at the end of this presentation that you get to go ahead and follow, and if you manage to complete some of them, there may be a reward waiting for you at the end.
And bragging rights too. That's what
and bragging rights too. Hey, write it on your resume. Actually, you can write this on your resume. Just saying. Okay, let's get started then. I have a page of notes I have to follow through, and again, for those of you who are watching this recording afterwards, you can follow along with the live demo, or I do have some videos. I kept the same videos as last time in case those may be more helpful to you. Those I recorded at my house, so it's like higher quality and whatnot. But for now, Sam, could you hit the lights? Turn on the lights. One of the lights. Oh, all the lights. No, I mean, turn on the lights so I can see. Okay. Okay. Oh, no. Okay. So again, thank you all for taking your Friday's time off to come learn about circuitry. I hope this will be a fun experience for you all. This first part, I'm just going to go over all the contents of the circuit kit. So what do you get? What did you pay $10 for theoretically, and what is in this thing? Well, obviously it's a circuit kit, so there's a lot of circuit components inside of it. We're just going to briefly go over what each one is, and you can go ahead and look in your own kit and figure everything out. So I'm just going to dump it all out and start with, should be on the side. Start with this. So this is a breadboard, and a breadboard is kind of like an electronic prototyping tool. A lot of electronics you see in like computers, phones, they come on a motherboard or some kind of PCB, a printed circuit board, that already has all the circuit components inside of it. However, if you wanted to make your own circuits, you kind of need a simpler version of that. And the simple version of that is the breadboard, with the wires to act like connections to components, and you can put like components on there. You're able to make your own circuit, and you're able to see your circuit live. So in that case, this is a breadboard, and you put the breadboard inside what's called a pocket breadboard. Now the surrounding frame is a pocket breadboard, or it's something I invented a while ago, just for the funsies. I decided that for those of you who are ECE students, you usually have to buy a large breadboard, and it's like a freaking huge one, and it's like really hard to carry around. That large breadboard has these 5 little things called terminal blocks where you can plug banana plugs into in order to test your lab equipment, kind of like this. But, the small little breadboards don't have that, so I decided to make a frame for it, and now we're here. So you guys get to go ahead and in the lab use this tiny little breadboard to be able to plug, power supplies in and get your circuit running and whatnot, and it's other cool stuff as well, without having to, bring a giant breadboard. And, even after the workshop, you can carry this around, use it in your labs, use it in your daily life, use it for testing, whatever the case might be. So I think it's pretty cool. The next thing we're going to go over is these little chips. Now these chips are known as IC chips, or integrated circuits. The other name for this is DIP, or dual inline package. These are logic gates. So in the circuit analysis workshop last week, we covered a little bit about digital logic at the end of the workshop, and what it is and how to work with ones and zeros to create some sort of like computing logic. Digital logic, you can step it up to build full-on computer architectures and cool things like that as well. So in this case, we have some AND gates, OR gates, inverter gates, NAND gates, NOR gates, XOR gates, XNOR gates, 7-segment decoders, D flip-flops, and I think that's it. So you have 8 chips in here, which are the most common digital logic chips. And let me tell you this, if you were to buy this from like an online supplier, each one of these chips would be like $1. So basically this bag here would be like $8 because there's 8 chips in here. But if you're paying $10 for this, I think it's a pretty good deal with everything else. And if you're a high schooler or if you're an IEEE member, you get this for free. So again, great deal. Anyways, moving along. These are LEDs, also known as light emitting diodes. LEDs are like the most simplest component that is like really exciting to use because they light up, right? You can actually see something happen to them. So pretty much if you feed a voltage through an LED and it's above the voltage threshold needed to turn it on, for like most LEDs it's around like 2 volts, 2.7 volts, whatever the case may be. If it gets past that, it'll light up. So I think that's really cool. And the thing about LEDs is you never want to put too much current through them because, if you don't put a resistor with an LED, it tends to go kaboom sometimes, or heat up, or smoke, or nothing. Wow. It just like dies. Yeah, so make sure you treat these nicely. These are pretty cheap. I think, in the market, they're like ½ cent.
Nothing.
So, pretty cheap stuff. Next, we're gonna go over this bag. Now these are resistors. Resistors resist current. It's in the name. So it prevents too much current from flowing through your circuit, and it acts as kind of like a barrier for short circuits. It doesn't let too much current pass through your circuit. Now, there is a possibility for these to catch on fire or burn or whatnot too. If you have too small of a resistor and too high of a voltage or too high of a current passing through, it starts to glow, it starts to heat up, and it'll burn you if you touch it. So be careful. But these are really cheap components, even cheaper than the LEDs. Like one resistor is like $0.25 cent. So
I think you can buy just one resistor.
You can't just buy one resistor though. Let me just tell you that. It's impossible or almost impossible to buy one resistor, and like the shipping cost would be just insane. So yeah, we gave you the most common resistor values. There's 330 ohms here, 1 kilo ohm, 2 kilo ohm, and 10 kilo ohm. So these should suffice for now, but if you want more specific values, you can buy a resistor kit online for just as cheap. The next thing we're gonna go over are these. These are buttons. My mistake last time I held this workshop was not defining or not showing you guys how to use these buttons, because this was like the main confusion for everyone. And these buttons are cool because they come in like 8 different colors. There's 16 of them in this bag. Also a pretty cheap component, but more expensive than the others. I think it's like $0.01 a button. But we're gonna go over how to use these buttons and how you can build circuits with them. The next thing we're going to go over are these. These are capacitors. Now you got to be careful of these because feeding too much voltage through them will cause them to explode. These are electrolytic capacitors, which means that they are polarized. They have a specific positive and minus side. The capacitors, again, are pretty much storage devices that can store electricity. And if you have big enough capacitors, that's called a supercapacitor. And it discharges very quickly through some kind of system or a load. And again, you can think of capacitors kind of like as batteries. They store charge, but in this case, batteries store charge chemically, and these store charge in using metal plates. Again, also very cheap components. Dielectrically, yes. Also very cheap. Yeah. Next, we have this bag. This bag contains a 7-segment display, which is kind of like what every ECE student eventually uses. It's a very simple display to understand. We're not going to go too deep into it today, but pretty much it consists of 7 LEDs, or 8 if you count the decimal points, that light up based on which pin you feed voltage into. There's 2 types of 7-segment display, one being like a common anode or a common cathode. Just depends on which pin you connect to common ground or VCC. But it just shows stuff. It's a really cool little display mechanism. The other chip in here is a 555 timer. Again, a very common component in electrical engineering or just circuit design in general. It acts as kind of like a clock. So you can make a clock, you can set its PWM or pulse width modulation. You can change the shape of it. It can only do square waves, but it's a pretty cool and versatile piece of technology.
Very useful chip.
Very useful chip, yes. The hard challenges that if you are experienced in circuit design, some of the hard challenges include this chip too. Okay. Oh, also I gave you 2 breadboards because,
breadboards go bad.
Breadboards can go bad very easily, especially the ones that are in your kit. The most expensive breadboards, BB830s?
Yeah, those, and then also the ones from Adafruit. I guess they sell those as well.
Well, Adafruit just sells very expensive things, but breadboards are there's like two sides of breadboards. Either you get very expensive breadboards, they work beautifully, or get very cheap breadboards, and they sometimes work, sometimes don't. That's why I gave you 2 breadboards, just in case one breaks, you can get the other one. But so far, I don't think we've seen any breadboard failures. I will tell you that I got these breadboards for like $1-ish, so I think it's
okay.
It's a pretty good price, but I wouldn't say the best of quality. All right, the next thing we're going to go over is this cable. Now, the reason I included this in the circuit kit is every electrical engineer I've ever talked to needs one of these cables, but can never find them, especially if they're an introductory engineer. It's a very useful tool used in labs mainly. You plug this into lab equipment, and then you can use these to test, or you can plug this into a power supply and use this to test, or a multimeter and use it to test. It's very useful. It's also very long. This side's called the banana, and this side's called the alligator, right? Because, you know, this kind of looks like a banana, and this kind of acts as an alligator. Don't do that, it hurts. So use this. You can use this at a lab. You can use this afterwards. I don't mainly use it if I'm just doing like, you know, like local stuff without a lab, like doing something remote. Some may have a different opinion, but this is very useful in lab situations.
I know that's been fun. I mean, I have a pair, but it stays on this.
Yeah,
it doesn't move.
Yeah. So what Sam says, I do have one as well, but it stays on my power supply, and I don't move it.
No.
Okay, next component we're going to go over are these cables. These are jumper cables, specifically DuPont connectors, and the name DuPont is just the guy who made it.
They're the guys who fund the race car stuff too.
Yeah.
DuPont? Yeah. No,
DuPont.
DuPont does a ton of stuff. They're like 3M, and they do a bunch of different things. But yeah.
So DuPont is really cool. There's 3 types of cables here, and you know, we call either end. Basically, we characterize the end by saying it's either male or female. If it's sticking out, it's male. If it's you stick something in it, it's female. That's pretty much what it is. Yeah. So there's 3 types here. One is male, so both sides are male. This is useful for building breadboards and whatnot. Mm-hmm. And then I also gave you some female ones. These are good for if you're plugging them into breakout boards or sensors that have male sticking out of them. Like if you're dealing something with sensors, especially, or like even drone stuff, like PixHawks, you need female wires because that's just what works and what you plug it into. And here you have male male on one side, female on the other side. Again, all these 3 types of cables you might need in the future. I found that as I was learning engineering that I didn't have one of these cables. So like, I think it's really useful that you guys have them now. Just so in the future, if you might be working on a project and you think that, oh, I need like a male-female cable, you can just reach into your circuit kit and get it. So it's a really useful tool. And also just connects electrical components together. Current just goes through it. It's a relatively simple component to use. And the last one I have here are these terminal block. Oh, actually, I'm going to take these out because there's a lot of stuff in here. So first of all, you have your SPDT switches. These are little tiny 3mm SPDT switches that I provided for you.
Should you explain what SPS?
Yes. Yeah. So SPDT stands for single pole, single throw, which means that there is one input and one output, technically.
Then there's double throw.
Single pole,
double throw, double pole. There's a bunch of different stuff there.
A whole bunch of combination. It's really cool. Mm-hmm. But here we have single pole, single throw. So pretty much this switch works by having this little top knob go back and forth. And pretty much the center is always connected to something. It just depends on whether you're shorting the left 2 pins or the right 2 pins. And so if the knob is on the left side, you're shorting the left 2 pins. And if the knob's on the right side, you're shorting the right 2 pins. All right, we'll go over this more in depth when we're making the circuit. The next part here is this thing. This is called a terminal block connector and pretty much allows you to interface your breadboard circuit with the outside world. It's also useful for connecting things like power to it, like external power supplies, because it's safer than just sticking a wire into the breadboard. Now you'll see that this terminal block connector has screws on the top. Now this allows you to put some wire in and then screw it shut so that you can't easily remove it. Again, really useful for power because whenever you're working with a power supply, you always run into the danger of shorting it somehow. So with you having just to put the wire directly in, screwing it shut, and not being able to pull it out, you have a very secure connection, and you can just basically guarantee that you're not going to, short a wire accidentally.
Better pre-built power supplies use those than the other more common terminal screws where you literally just unscrew it from a base plate and just shove it in. Those are not as great.
Yeah, if you see like bare wire anywhere or like metal, like on like something power related, that's kind of dangerous.
It's kind of scary. Yeah.
All right, and the final piece, actually, this is kind of like the most expensive part out of all of them, just because of like what this is. This is a potentiometer, and to be specific, it's a 10,000 ohm potentiometer, or 10K 104. So this potentiometer is special because when you turn the knob, it changes the resistance inside the device. I think that's just pretty cool. And the reason it's so expensive is just because there's this little knob there you can do handheld stuff on. There's different kinds of potentiometers, like some have like really tiny dials that you gotta use a screwdriver on, and some are just like too huge. But these are perfect. You can put them in a breadboard, and they're very small, very compact. Anyone want to guess how much this was? Retail, that's a little bit expensive actually. Like all these components are under $1. Almost, yes. So this is 45 cents. And you know, if I'm saying like this is the most expensive part of all of this, you got to know that this is like something special. Like you don't find this anywhere else. A lot of potentiometers, or the common ones you buy off Amazon, aren't breadboard compatible. So you got to, figure out one that is, which is this one, or you get the really small tiny dial ones that are like annoying to work with.
Right, with the screw terminals on them.
Yeah, with the screw terminals on them, and they're just a pain in the butt to work with.
Yeah, they're terrible.
Yeah. So I've gone through everything in the main kit. Are there any questions as to what something is before I move on? Yes. Oh, yes, I will explain that later. But just in the kit right now. No one? All right, we're moving on. So let's move on to this one first before I get into like the, well, that's not good. So before I move on to the little plastic piece here, let me explain what this is. Now, if you were here from the previous Season 3 workshop series, we actually pretty much designed this board inside the workshops. We designed the PCB in 3x04, I believe, which is PCB Design Workshop, and we designed the case in 3x05, which was the CAD workshop. And then we printed this case in 3x07, which was the 3D printing workshop. So literally this was kind of like Season 3 in a nutshell. But again, it's another one of my inventions. It's actually a portable power supply, which I think is pretty useful if you're just bringing this around with you. You want to power an Arduino to test some code. You don't have to lug a big giant power supply around that you plug into a wall. It gets power from a 9-volt battery. You have about 1 amp of current drawn from the battery at all times. It's good for like testing microelectronics when you don't have like a power supply in the wall. So how you use it is pretty much, it comes with 3 switches that are the user inputs. When you switch one switch, the leftmost one connected to the wires, the green LED will turn on. This means that your just circuit will work. This is the on-off switch for the circuit. The middle LED turns blue, and this is going to be connected to a 5-volt source. Now, a lot of electronics use 5 volts. This is called 5-volt TTL, or transistor logic. A lot of Arduino's power gets used power from 5 volts. A lot of ESP32s, Raspberry Pis. 5 volts is kind of like the standard, but just don't power Raspberry Pi with this, because Raspberry Pi needs about 3 amps ish, and this can only give 1 amp. So Arduino's would be the best one to power from this. And again, you have a terminal block here, so you can put like DuPont wires inside of it and then connect it to your circuit or your Arduino or whatever the case might be. So it's really cool. And this one down here is 3.3 volts, or what I like to call the second most common TTL logic in electronics. This powers things like wireless communication. You can also, ESP32s also accept 3.3 volts.
Some microcontrollers take 3.3.
Yeah, some microcontrollers take 3.3. That's correct. Yep. So here you can see we've regulated the power down from 9 volts to 5 volts to 3.3 volts, and the terminal blocks allow you to use that voltage in your circuit. So it's a very compact mechanism, and again, in here is the 9-volt battery. This on-off switch turns off everything, and you want to make sure you do this before you don't want to just leave these LEDs on. That's kind of like the indicator, because even if there's no LEDs, the circuit will still be using power from the 9-volt battery in a phenomenon known as parasitic power. Parasitic power is a phenomenon where you have some leakage current that goes through your circuit even though it's turned off, and you don't know. So if I turn this on and left it, or even if I turn it off and I leave it for like a year and come back to it, the battery would be dead, because a small amount of current travels through the switch and into the circuit using up power. So this is basically the safest way to not use power, just to disconnect the battery, but this is the second best way. So everyone know what this is now? Anyone have any questions? Yeah. Don't worry about that. Some of them are. So let me tell you this story. We spent basically the entirety of yesterday putting these together, and basically students soldered all of these boards. So there's going to be some user error. but we've tested all the, as long as the LED lights up, you're good.
Yeah.
They might not be like perfectly green, blue, yellow, but you know.
The colors don't matter.
Colors don't matter.
If it lights up at all, that means it's probably working.
Oh, that doesn't light up?
At all? It doesn't at all.
Well, we're gonna check that one out later.
Yeah, that's yeah. Kind of ensure that your guys' circuits work, because if they don't, then
yeah, this would be a good time to just test out if this module works and you get all 3 LEDs lit up. Because if the last LED doesn't light up, it's probably because the LED was soldered on backwards. But I can fix that.
you did check voltages on all of them, right?
Well, that's what we're gonna do next.
Yeah.
Do we have multimeter? Don't have one. Okay, so to verify that everything works, we're going to be testing this using a multimeter, but Sam is going to go grab the multimeters right now for us to test with. Meanwhile, let's go over the last component in this kit, which is this. Now, this is basically one of my inventions. Again, I found it really difficult to cut resistors to size when putting them directly in the breadboard. So pretty much this is a 6mm thick plastic little design I made in order to facilitate that. So when you cut resistors and put them in the breadboard, you don't want them sticking out because you can short the wires or you can just cause some internal damage, whatever that may be. So this allows you to prevent yourself from doing that. So I'm going to go ahead and actually just take some resistors out, take like a 330 ohm resistor out. 330 ohms, by the way, is kind of like the most common resistor value in electronics. I don't know why, same with 220, but like every tutorial in the world tells you to put one of these resistors across an LED. It's kind of like the first project that you do. So we're gonna take a 330 ohm resistor and put it in the breadboard. Now, in case you don't know how a breadboard works, we're gonna like showcase that in a little bit, but just put it in as of right now with any 2 pins. It doesn't matter which 2 pins. Now you can see that this works. The resistor is inside the breadboard, but the problem is if we put another resistor in the breadboard, some weird things might happen, right? Because it's not neat. You might have some situations in which if I have another resistor in this breadboard here, and I don't carefully put this in enough, and I don't carefully manage it, some of the resistor legs will touch. And that's not good, because if something's touched when you don't mean it to, sometimes that can cause a short, sometimes that can cause a fire. I'm like boosting this up, but like usually fires don't happen. It's usually smoke. But just be careful about this. So the way I solved this was I went ahead and made this little component gauge. And this thing is called the component gauge. It's meant to help reduce your circuit mess. So what you do is you put this resistor, which is a 1/4 watt resistor, into these holes. And you're going to just take your wire snippers and cut the bottom. Like this. And I know you guys don't have any like wire cutters as of right now, but in the lab you will. So as of right now, you guys can just put the resistors in. But you can see that when I take this resistor out, this will be the perfect length to put it inside of the breadboard and have it be flush. Have it be flush with the surface of the breadboard. I'm all about making your circuit neat, because the neater your circuit, the less pain it'll be for you to troubleshoot it, first of all. The less shorts you're going to have, the less fires you're going to have. Just in general, neat circuits make the world go round. Are we getting anything?
Yeah.
Okay, so Sam has brought over this tool, which is the most useful tool in testing electronics. It's known as a multimeter, and the multimeter can do a lot of different things, including measuring DC voltage, measuring AC voltage, measuring current. If it says A here, this measures DC current. So you can measure current that way by connecting it in series across the circuit. You can measure continuity and test LEDs. And you can also measure resistance. So right now, to make sure that my voltage regulator works, I'm going to go ahead and move this multimeter to the voltage mode. And these numbers on the side just means what scale you're measuring the voltage to. So the way I like to understand it is kind of like if it says 20 here, it just measures up to 20 volts. Anything above that, and it'll give you like a 1. If you turn it here, it measures anything up to 200 volts. Now remember, this is DC, so don't go sticking this into a wall or anything. And this measures up to 500 volts. Anything below that, this measures up to 2 volts, which is 2000 millivolts. and 200 millivolts. So the numbers just represent the scale. In this case, because I'm expecting my scale to be like 9 volts, I'm going to turn this to the 20 volt region. And I'm going to go ahead and put my little prongs here to the PCB. And we can see that because this is the input voltage, it says about 9.68, 9.69 volts. By the way, full 9 volt batteries usually come at around 10 volts. It's not actually 9 volts, it's a little over. So we verified that. So I'm going to go ahead and turn this on, and I'm going to measure the middle now. So when I measure the middle, you can see that it says 4.9, 4.94 volts, and it's actually negative. Does anyone know why it's negative? Yeah, I swapped it, right? So when you're connecting to the circuit, just make sure you recognize which part is positive, which part is negative. So my red one is on the positive, black one's on the negative, and it says 4.9, 4.96 volts, right? And the 3.3 volts, yeah, that's around the right region. Okay, so now that we've measured everything, just remember continuity matters. So just make sure you plug the plus into the plus and minus into the minus. Convention-wise, when you're working with breadboards, when you're working with this kind of stuff, you got to make sure that red goes to the plus symbol, and then black or blue go to the minus symbol. It's kind of like a convention. If you swap them, then you have to. There's nothing wrong with swapping them actually, but you just confuse yourself. You just confuse other. So just stick with red as positive and black as negative. All right.
Yeah, it's important to follow standards. Make sure that everybody's on the same page.
Yeah,
including yourself. Because the thing is that nobody's going to understand why you put the positive terminal on black, because that's just not how it goes, right?
Yeah.
It's not the deal. Yeah, well, I mean, that's true. And then sometimes they're not even colored at all. It's just the same line.
Yeah.
Yeah, that's why you typically just tear out the whole thing and just start over. So, yep, no, it's the same way. And that's even worse because you're working with like higher DC values where it's like to the 60 to 80 volt range, right? Because it's vamp power kind of stuff. Like that's a different deal. So much scarier.
Yeah. Yeah. And also when you're working with like live power, black is no longer ground.
No, because you're
black is death.
Yeah, black is death.
Black is live.
That's your death. Yeah.
So just keep that in mind.
Brown is death because like some of those death cables gone. Yeah.
Yeah. It varies per color.
Yeah, it does.
Yeah.
I'll get it later.
I guess another thing to kind of note though is that if you're ever looking at like AC plugs, as apart from like DC stuff, like direct current versus alternating current, your kit.
Your kit. Yes.
Yes. Basically the idea is that with AC, there is no positive and negative, right? Because it's shifting. It's going back and forth. It's kind of alternating or something like that. So it's not as important, but it's still just as deadly to not understand like why it would not work. You're never going to be working with something AC in this lab, I don't think.
No.
Or ever really with us, because
the amount of liability forms we would need.
Yeah, because that's like AC is mostly for like mains power stuff.
Yeah.
We're not going to be doing anything.
All right, so now we know how this works. We've tested it, we've verified it. Now we know how the component gauge works. You guys know how this works, right? You guys have any questions on it? So these are for like resistors, a 1/4 watt resistor and a 1/2 watt resistor. And these ones on the side are for LEDs, diodes, and other like components that will fit in. So if you want stuff to fit into your breadboard, like even a capacitor, like let me get an LED and show you right now. So for LEDs are polarized. Again, they're diodes in the name. So you want to make sure you're connecting the positive side and the negative side to the right place. For an LED, the positive side is the longer leg. So you always got to remember that. And the shorter side is the negative. So always, 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 if you want an LED to turn on, it goes from positive to negative, right? If you don't do that, it just won't turn on. So for LEDs and diodes and capacitors, all you do is you put it inside these side slots right here. And then again, you can just cut it. But for an LED, just make sure you cut the smaller leg a little bit shorter than the longer leg, because you just want to make sure that you know where positive and negative are. So like I cut it like this, and then I can put it inside my circuit here. If if it will let me. Sometimes you gotta break in your breadboard. Sometimes your breadboard just doesn't like you on the first try. So there you go. Now you can see that the LED is flush with the breadboard and you don't have dangling wires everywhere. If you have a breadboard that looks like just a jumble of wires, kind of like if you jumbled a USB cable and tossed it on the floor, that's called a rat's nest. You kind of want to avoid that. Rat's nest can exist in like all types of electronics, especially for your senior projects. Like if you're an electrical engineer and you go into your senior project, I don't want to see you guys have rat's nest, because I'm gonna let you know, I have worked in projects before where like I've looked at legacy work and it's just a pile of wires, and I'm like, what's going on?
Legacy work.
Legacy work, yes.
The work I did yesterday, like that work.
Sure. Yeah. So now that you know how the component gauge works, does anyone have any questions so far as to what we talked about?
It's okay to ask.
Yes, please ask, because it's better you ask now than later when you've like burned something.
Yeah. Does anybody not like understand something that maybe we have gone over, whatever the case may be? No?
You said the shorter legs.
Yes,
Correct.
Correct.
Longer legs positive, shorter leg negative.
As long as the positive is running to it,
yeah,
we should be fine.
You know
what?
You can also look at like what the LEDs on the inside, but like I don't look at that.
Dude, that's
okay.
Okay, but that sometimes isn't always gonna work.
Sometimes you can't even see it because for LEDs that are like very
plus,
dark.
Depending on the manufacturer, they change that. That's your silicon flap, and that changes. They change that. I mean, then just throw it away.
Good. Actually, I want to talk about that because you can test an LED with a multimeter. I don't know if you can do it with this one, but let me just talk about this right now. Can we hit the lights?
Yeah.
So, on the multimeter, there's this really cool thing. It's a diode right here. Oh, now the camera can't see anything. Just like half of it. Okay. So if you turn your multimeter to the diode symbol, what you can actually do is test LEDs by putting the positive and the negative side on the LED right here. So you can do this real quick. Oh, it just rolls around. All right. It's a little bit more controlled. You're correct. You are correct. There you go. You can see it light up a little. So the multimeter, what it's doing is just sending a small little voltage across an LED to turn it on. So like Josh said, if you like just cut an LED and they're the same legs, you can use a multimeter to test it out. In fact, this is also what I do for SMD LEDs. Like I can put the multimeters across. I'm not going to do it now, but like for like these small chips, I also test to make sure it works. And you don't need a resistor in that case because it's such a small voltage. But in general, if you're doing like 5 volts across an LED, please put a resistor. Okay, so now I'm going to go ahead and change it back over to the presentation here. And we're going to go ahead and watch a video on how to use a breadboard because I think in the video I had a specially, well, it's a special breadboard that I think would be a good thing to show. So let me go ahead and share sound. And here we go. In this video, I'll be providing a brief introduction as to how breadboards work. Breadboards, and this is a 400-pin breadboard, usually comes in 3 different components. In this case, mine comes with 2 power rails on each side of the breadboard and 1 main component where your circuit will be built. These side power rails are what provides power to your circuits. You have a rail for power, which is the VCC, which is the red, and a rail for ground. If we look on the back of a breadboard, and this is what a breadboard looks like if you uncover the back part of it, it's a little bit dusty, you can see that the power rails have all the vertical pins connected together, which means if you go ahead and put a wire into the top pin for the ground section, you'll get the same signal on the very, very bottom. Same for any other location on the vertical rail. This is because all the vertical rails are connected together via 1 strip of metal, which means they're all connected with each other. If we take our multimeter, switch it to the continuity test mode, we can see that the top portion of the breadboard for this rail is continuous with the bottom section. That little beep you hear when you hear the continuity test means that it is continuous. Same for the power rail and all the other side rails as well. So when you're building your circuit and providing power to your circuit, what you can do is you can provide power and ground as one component of these, at one pin of these side panels, and it will provide power for like the entire vertical area. Same for the right side. Now, the left and right side of the power are not connected together. Therefore, if you want to access the power from both left and right rails, you'll have to put a wire connecting the left side and the right side together. Now, be very careful of short circuits because this is the part where a lot of mistakes can happen. The red always represents your VCC, your voltage common collector, your 5 volts or whatever voltage you're coming from. The blue side always represents ground. So if you follow these conventions and you don't connect anything backwards, you'll always stay safe in your circuit. But just keep that in mind because that is usually the best way to stay in check with whatever voltage is coming out. When you're if you connect something with reverse polarity, which means you connect ground to the red line or 5 volts to the blue line, you'll get very confused later on as to why your circuit is smoking. So the best way to do that is just to make sure that your VCC is always on the red line and your ground is always on the blue line. That will eliminate a lot of errors initially. Now you'll notice that the main part of the circuit is connected a bit differently. All of the horizontal sections are actually connected together instead of the vertical sections. Therefore, if I had some sort of signal on this row of the breadboard, I would get the same signal on the same row but on a different pin. So everything in this row is connected together by a metal panel on the back. So for example, if I can take a continuity test of each of the rows, we can see it is connected together. That sound just means like you have a connection between those 2 points. You'll see that we have a little bridge in the middle where there is no metal connection. Therefore, if I put a signal on, let's say, row 12 on the leftmost pin, it will not travel to the very rightmost row of the 12th pin. Therefore, you have a lot of options when connecting circuits together on either side of the breadboard. So, as a recap, for the power rails, all of the vertical pins are connected together. For the center part, all of the horizontal rows are connected together. And it is very obvious to see that when you're looking at the back of the breadboard. This has been a brief introduction of the breadboard and how it's used, and I hope you enjoy using it. All right, so I obviously don't use this breadboard for building circuits anymore because, you know, that'd be very dangerous. It's like you're holding the breadboard and get shocked because you're touching both power and ground rails. Do you guys have any questions about this video before we move on? Yes?
Why does it really matter? Because both for the positive and negative fields, they're just both just metal strips.
Right. So they actually don't matter. But, you know, if you don't set one as power and one as ground the entire time, you're going to get confused when working with like other people. You kind of have to like label like where your power is coming from, right?
Mm-hmm. Well, I mean, yeah, because that's like the whole thing, right? Like the convention is there, and you should follow it. But if you don't want to, that's fine. But the thing is that it's probably good. It's probably there are other people who are probably going to get mad, like me, and the other thing is that you're probably just going to get mad at yourself because, like I said, you may not make a mistake then, but you revisit the circuit later, or you look at something like that, you're not going to understand like what's going on, right?
Yeah. It's best if you follow the convention in this case. It's less confusing.
There's a reason that standards exist. That is actually one of the sponsors for today's IEEE. They actually make standards. Like,
yeah.
all this stuff. That is their job.
Yes.
To make standards. So standards exist so that we don't have to argue as much. So.
Yep, that is correct, Sam. And yes, the sponsor of today's workshop, one of the sponsors, is IEEE and IEEE NTC, which stands for Now Technology Council. Yes. So if you have a circuit kit free of charge because you're an IEEE member, you can thank them. Okay, let's move on. Now for the fun part, we're actually going to connect power and ground to your circuit. Now again, remember that the power and ground, these are called rails, by the way, because it's kind of like a train track or a train rail where it goes like from a very long distance. So just notice that everything on, let's see, all of the vertical parts are connected together. I'm gonna use this as a pointer. Okay, so all these vertical pins are connected together, which means we're gonna go ahead and put a power wire, a DuPont connector, to this pin right here. Right? Now, if I connect this to my power here, then every single pin down here will also be connected to power. Does that make sense? So in order for you to get a complete circuit, again, we talked about this in the circuit analysis workshop, but you need some kind of power supply, and you also need, anyone? A ground, yes. So we're gonna put a ground pin, which we always, for the most part, I wanna keep it as black so you guys can understand. But you guys can use like yellow or like brown or whichever colors you guys you want. But just make sure you know that it's the ground. Because, mistakes are kind of like costly in the world of electronics. Okay, so now let's go ahead and showcase the utility of this power supply. Remember that the middle is 5 volts. So we're gonna go ahead and connect these male pins to the 5 volts. Now, unfortunately, you guys don't have screwdrivers. But fortunately for us, we can just plug them in, and for the most part, they'll get a good connection. But I'm gonna go ahead and screw them in real quick. All right, a fancy little electric screwdriver. It kind of looks like it was made from Apple. There we go. Again, the reason we screw them in is just because it's like really hard to take apart, and you won't actually like drop this or like short it or whatnot. So in this case, what we're gonna do is if we flick this switch and the blue LED turns on, then that means this circuit is being supplied with 5 volts power, right? Which means we can then go ahead and power it on an LED. So let's go ahead and build a simple LED circuit, right? Now, in order for an LED circuit to occur, a few things need to happen, and I don't have a black pen, so I apologize in advance. But the basic LED circuit is going to look like this, right? You have your power supply that looks kind of like this source here, and then you have a resistor. And why do we always have a resistor for an LED circuit? Yes, to restrain the current. Yes, exactly. So we don't blow up the LED. Now, a lot of times we have the circuit symbol for an LED as this. And these arrows just represent that there's light coming out. Now, this also may represent like a photoresistor. If you have anything that deals with like light or luminosity, you always have the symbol in store.
You can eliminate more than just stuff you can see. So there's like IR LEDs that exist, and those illuminate, or UV LEDs, which eliminate UV. Don't look at the UV ones correctly.
Yeah, so we're gonna use a 330 ohm resistor here. Okay, and a 5 volt power source. Now, just a little trivia question here.
330.
Yeah, why not? Who can tell me how much current's gonna pass through this device, this LED? Assuming that there's no current drop. Okay, I heard like 2 different things. So let's see. What equation are we going to use? Ohm's law, right? What's Ohm's law? V equals IR. Now, because this is a series circuit, we know that the current travels through the entire circuit in the same way. And we're trying to calculate current, right?
No nodes.
There's no nodes, no anything. This is like the first circuit you see in 1101.
Man.
So we're going to calculate current. So it's just a little bit of algebra. I equals V over R, right? And in this case, V is going to be 5 volts. R is going to be 330 ohms. And what's the result of the calculation?
You don't have to do this in your head, guys.
Yeah, use calculator.
Just use a calculator. Use your phone or something. I don't know. Something. First time in a long time using the phone calculator.
0.015.
What is that in? Like, what is the unit? Yeah, amps.
Well, it's amps, right?
Yeah.
But in general, we don't write,
Well, it depends. Yeah.
This is like really small and really hard for us to understand a lot because current is generally very small in a lot of components.
In our deal, it is.
Yeah, if you get to like big currents, then it's scary.
Yeah.
Big currents are scary. Again, 1 amp can kill you. So in this case, we can rewrite this in milliamps. And what is the milliamp equivalent for this number? 15. Good.
We did that because we moved the decimal place back 3 places.
Yes, so
milli,
1, 2.
Yeah.
Mhm.
There's, in any of this kind of stuff for significant figures, we typically like to work in threes for that kind of thing. So milli, micro, pico, those are all kind of like giga, 6, you know, like
Yeah.
we don't really like the ones in between because nobody really cares. So,
I think it's actually called like engineering notation or something.
yeah, or just, it's just called common sense. Yeah,
Engineering common
yeah,
sense.
it's just common sense.
All right.
Yeah, yeah.
Okay, so let's build this circuit now. Should be pretty simple. Again, when we're building a circuit on the breadboard, we're basically just replacing all of these like intermediary wires with jumper cables, right? So what I'm going to do is I'm going to follow this circuit almost exactly. In this case, our power supply is pretty much just a plus and minus wire. So in this case, I will just label here as plus and this as minus, right? So this wire or this connection here, I'm just going to use the word connection, goes from the positive end of the power supply to the positive end of the resistor here, or to the start of the resistor. Resistors aren't polarized, you can flip them and they'll work the same. But in this case, we're going to take a circuit from the 5 volts and we're going to connect this to one of the one of the ends of the resistor. Now you can do this either using a cable, or what I'm going to do is I'm going to go ahead and just directly connect the resistor to the 5-volt rail. Oh, also, I almost violated. Actually, I didn't violate a rule. Make sure you turn off your power supply before editing your circuit. You know, just because you don't want to accidentally plug something in, having something's gonna screw up. Yeah. So, luckily, I didn't have the middle one turned on, but like I'm just gonna turn all of it off. All right. So I'm gonna.
Yeah. Always turn it off. Always unplug it from the wall.
Yeah.
Always do what you need to do.
Okay. So now that I've used the component gauge to cut off my resistor, so it's nice and flush. Sam's seen my circuits.
Yeah, no.
Connect one to the positive and one to the
Just another bar, just
Yes,
a bar.
just
Yeah,
another bar.
Yeah, just
because
a bar.
remember what we talked about in the video here? Where else is going to be connected to this end of the resistor? What's connected to the end there?
So
Or like
right,
electrically
sorry,
connected.
yeah, like of this rail.
Like if I put my continuity test here.
What other pins are going to be connected and going to have that exhibit? Yeah, the verticals.
Yeah, so it's right here, right? So this row.
Horizontal.
Well, we call this horizontal and then vertical, but yeah,
It doesn't matter.
it's like
On the other side, yeah, the positive side, you're experiencing your 5 volt on this side, and then yes, he's right.
Oh, you're right.
Yeah, you're right.
I was talking about the
Yeah,
left
yeah,
end
yeah.
though.
Yeah, sorry.
This end.
After the fact that it's been resisted. Yeah. Right? So it's like, so that's going to be experienced on which side? This side.
Yeah. Okay.
But only before the bridge, not like on the first and
Right. So after the resistor, then it will experience that resistance.
Okay.
Yeah, that's correct.
All right. So in this case, we've connected one of the wires already. So this was the wire we just connected. Now we're going to go from the end of the resistor. Actually, I'm going to put a pulse there. I'm going to put like point A. We're going to go from point A to point B, right? This is going to be the beginning of the end of the resistor, sorry, to the beginning of the diode. I forgot this camera. Okay, so we're going to go from the end of the resistor to the beginning of the diode. And also we have to consider where the diode ends up, right? So the end of the diode actually goes to ground, right? If we say point C here. So when we place this component, we have to go from point B to point C, in which point B is connected to the end of the resistor, right? Okay. So we can just get the LED wherever the LED went. There we go.
I'm going to wait until somebody screws up and it's knowledgeable like you. I will point out something that's very important.
Okay. So we are going to put just an LED. I'm not going to cut this one. This is going to be a yellow LED. Actually, I'll put a red one because it's easier to see. And you know, you can go ahead and connect it from the end of the resistor to the rail, but you know, I can't really reach. So what I'm going to do instead is I'm just going to plug the LED into the board like this, right? And then what I'm going to do is I'm going to take another wire and just connect it from the end here directly into the board. Okay, so, oh, I just didn't even plug it in. Okay. You guys can see this, right?
And the LED's in the same row as the resistor and, okay, I see.
Yes.
Yeah.
Is that okay? So now we have a complete circuit.
Positive side, right?
Longer side is the positive side, yes.
Yeah.
As long as that is the positive side. Okay, now if we turn our power supply on, we should see the LED light up. And it doesn't. So what happened? Ideas.
I caught it pretty quickly. That's why I rushed over here, but I realized he actually did it on purpose. So I was like,
yeah.
What was the question?
So what's wrong? Why isn't the LED
why is
lighting
the
up?
LED going on? There's power going through it. What's the deal?
No, the connections are correct.
Connections are good. Yeah.
Is it just like
The LED is what? Like it's, what do you mean by swapped? Yeah. there
Yeah,
you go.
you're right. So the answer was I put the LED in backwards, and this is going to happen to a lot of you, right? So remember, the longer side is positive, so the longer leg should go to the resistor instead of the jumper cable, right? So if I put the LED in this way, and remember your power supply should be off at this point, right? And turn it back on,
Yeah.
boom, we got a LED that lights up.
That thing is hella bright.
These are super bright LEDs. Let me tell you the story of this, right? Most of these components I bought from an external supplier. And the problem with that is a cheap Chinese company made these. And, you know, sometimes you might not get the quality you want. And for some reason, these LEDs are super bright LEDs.
That was what I was expecting somebody to say. Okay, so what's your name? What's your name? Okay. There was a mistake that was made that I expected was going to happen. That's okay, because I wanted it to happen, right? Can I see your circuit for just a quick moment?
I'm going to put it.
I'm not going to make fun of you too much, but I'm just doing it because it's important, and this is something that everybody, including like electrical engineers that have been working in this field for like 2 years and probably should know this, don't. Okay. So the idea is that if you guys look at it here, you'll notice that the LED, you know, it's corrected kind of, like, you know, the idea is there. I don't know why.
The yellow one's
Yeah.
covering it.
That's kind of annoying. There you go. The idea is there, but the problem is that they're all on the same bridge. Why do you suppose that doesn't work? Despite the fact that I can turn the thing on, and I give it supply. Why isn't it turning on? So that's a start, but there's something else that I'm kind of looking for. I can even draw it here too if you want. Right? If you guys want. What do you guys think? Nothing? No idea?
Yeah, drop.
Draw? Okay. Let's talk about the idea of something called a short, right? And shorts are something that we usually have to kind of go over. It's a very important concept in electrical engineering. So if you look at it here, right, the way that he has the whole thing set up, this is one singular lead, right? It's all on one. And in order to create that kind of potential, you need to have some kind of like thing that basically runs across it. Now, this resistor's fine. There's two different bridges here. You have two different terminals that are not connected in any way unless you go through that resistor, right? It's not going to work, right? Like you can't go anywhere else but that. But as we start to move to the diode, we'll notice that it's actually on the same leads. Now remember, since the diode is exhibiting on the exact same lead, there is a, you know, this is your diode, sorry, this is really bad, right? So emitting a diode and everything like that. We know that this is going to be connected, right? Because that's just a single lead. But here's the problem. Now you have two different paths that are split up right here. You have a node, right? Where do you think the power is going to flow in this case if it had to choose between the LED and that path, that path, the underpath, right? We call that a short, okay? Electricity, and maybe you guys have probably heard of this because, you know, your parents told you not to play near power poles or something like that, I don't know, right? I mean, my parents told me that. The idea was that electricity will always travel the path of least resistance, right? And since the resistance of these metal bars that you see inside of these, you know, breadboards are, of a lower resistance, right? Because they're just these solid metal pieces. The LED 100% is going to have a higher resistance. So because of that, none of the power is actually going to go through that LED because it's you didn't separate it, right? You're not forcing it to go through that area. So how do we make it so that this LED works in this case? Get rid of that, right? Sorry, I ripped it because I hated it so much. Say what now?
What did you do with the resistor where like it's on the same lead, like
Absolutely, yeah. If you do the same thing with the resistor on a single lead, yeah. No, you won't exhibit that resistance. If you made this mistake with the resistor, but the LED was fine, you would have blown up the LED. Because the thing is now you got 5 volts running through it, right? Because, you know, it's just, you went right through, right? Solid 5 volts, no problem, right? So shorts are important for a lot of different reasons. Sometimes you want a short, right? So for instance, like a switch, like a single throw, single pull switch, that is just a short, right? When you connect two things together, you are shorting the connection together, as vice versa, it is not. In electrical engineering, we call that a closed circuit or an open circuit. What do you think a closed circuit is? Yeah, right, it's completed. Everything is all together. Everything is terminated. Everything that you want to work is enclosed in that circuit. Now, there can be parts of the circuit that cannot be powered on. For instance, in Chris's little funny circuit here, I can technically turn on this thing and not necessarily have one of the circuits closed. So that means that there's no power running to it, right? And vice versa. So do you mind if I fix this in front of everyone? Okay, cool. So how will we fix this? How do you propose, once we kind of understand how this works, how do you propose that we fix this? What do you think?
Put one of the ends of the LED onto a different.
Good idea. Okay, so maybe we should also move our terminal block as well, right? So to maybe some other things. So let's try to see if maybe we can move it over here. Okay, this is our negative, right? So let's just pull it out, just make sure that we're good. Okay, cool. So he actually did me a favor, made sure that the long lead is, you know, actually the longer lead and the other one's the other. So if this is that actually negative on this thing? Do you know for sure?
The black one is positive.
The black one is positive. Okay, no worries, no worries. Just needed to make sure because I didn't want to blow up your thing. So obviously, if the positive is the black wire, which is feeding into your red here, then that means that the long lead is going to be what? Up or down? It's going to be on the upper layer, the bottom layer, the longer lead. What do you think? What do you guys think? Longer lead? Up or down? Up. Up. That's right. All right. If I could actually get the thing in. There we go. Okay, do you guys think this will work?
No, don't we put the resistor on a separate lead as well?
No, actually you're good. You're good to go. Because if we power this puppy on, here we go. You're good to go. Yeah. Just making sure. Yes. Yeah. Just making sure that you. Okay. Cool. Yeah. Thank you. Don't I make a mistake? I promise I'm not making fun of you. It's just I'm telling you because believe me, dude, there has been people in my major who have made that mistake on much more expensive equipment than just a single little Chinese LED kind of thing, right?
It's great to make mistakes now.
It is. Yeah, especially when
later.
yeah, because if you make the mistakes 4 years after you're an electrical engineer, I will make fun of you. So what's going on?
So the negative side is always.
Yeah. So there's a lot we can talk about that. So the idea behind what's called physical flow of current versus the theoretical flow of current kind of thing.
We did talk about that last time.
We did talk about that last time. I'm TLDR. You can actually say that the power is coming out of black and then going into red, or you can also say the power is coming out of red and going into black. Yeah.
It's just what convention you want to choose.
Right.
Like in reality,
It's
the
actually
electrons
coming
go
out
from-
of black to red.
it goes from negative to positive.
Yeah.
But since scientists have used positive and negative for so long, that's what we're sticking with.
Right.
So we're just going to assume that current always flows from the
And
positive.
and that you can choose. That is totally up to you. It's just that when you are running your calculations and stuff like that, you need to stick with one, and that's what you got to do the whole way through. Because if you swap midway, you're going to come up with some really weird.
Some professors
problems.
actually use like
Yep.
the negative. It's really
It's
like
really weird, and it's
Yeah.
kind of stupid, right? Because it confuses the heck out of a ton of people. But yeah.
Yeah.
Let me get the next thing.
Okay. So now that we've discussed how to make a simple LED circuit here, I have my notes here. Yeah. Are there any questions before we move on? No questions? Okay.
Or maybe no connection at all, too. That's another thing.
All right, now we're gonna move on to switches and buttons because I think those are fun. Now, it's really important you understand how switches and buttons work because it's kind of like the first gateway for user input. I just already done it. So switches and buttons are kind of like, again, they're essential electrical components, but they're kind of deceiving because you don't really, like, they don't really express themselves very clearly. So a switch kind of has 4 terminals, right? And we're going to use a button first. So a button has 4 terminals, your SPDT switch has 3. So we're going to take out a colored button here. Right. So we see this little button here. This button has like 4 terminals and 4 little sides. And we're going to go ahead and just draw that out right now on the paper, right? Like this, right? Okay. So what does the switch look like internally? Most of the time, you will put a switch across the bridge of a breadboard, and it usually fits really nicely there. Because a switch kind of looks like this, where you have the top 2 are sometimes shorted together, sometimes not shorted together, depending on your manufacturer. But the most important part is the middles are always switches like this. So all you gotta remember is when you're putting a button inside of a breadboard, the diagonals will connect, right? Or you can put like on the other side as well. But I also just basically assume that, you know, this switch is basically something like this.
Yeah. Current
Current will flow in the diagonal direction across this button. So when you press the button, current will flow like that. Okay? I don't know if it's focusing or not. This camera doesn't like focusing. Are there any questions before we go to the physical demonstration? So buttons connect diagonally. Yes. Oh, okay. All right, cool. So how do we implement a button into this breadboard in order to turn on this LED? Okay.
I'm actually kind of curious how Chris will do this.
I'm actually curious on how I will do this too. I have Oh, there's the LED. Okay. So we know that the button will electrically connect things diagonally, right? So I'm going to take away part of my circuit first. Basically, what I'm doing is I'm saying, where can I break my circuit in order to insert this button? Because from this circuit right here, I can either put the switch right here or on this side, right? Actually, I'll let you guys choose. Where do you want me to put this button? Let's say X or Y. X, I heard X first. So we're gonna put the switch here, which means we need to disconnect the 5 volts and the 330 ohm resistor, right? Actually, that makes things more difficult, which is fine. I have to reconstruct some of the circuit. Okay, it's okay though. So what we're gonna have to do is we're gonna put the button between the 5 volt power and the resistor. So I'm gonna just disconnect everything first, just to prime things. And I'm gonna also disconnect the resistor. I have fat fingers, I can't just pry it out of the breadboard in my hands. It's pure enough. Well, if you want real, like
two layers of safety.
There's 2 layers of safety. It's like a double hinge. Okay, so we're gonna go ahead and connect the power. So we're gonna assume that the thing is powered on. You can't see this. And we're gonna connect it from the 5 volt rail down to, let's say, row 5, right? And in my mind, I'm going, how can I make this thing electrically conductive throughout the entire thing? Because remember, it's kind of like a maze. We have to get from 5 volts to ground, right? And once we make that connection, our LED will turn on. So then I'm going to go ahead and put a button across the bridge. This is usually the most common way to put a button on a board, by the way. Good question. So you'll see that one of the corners of the button is in the same row as this jumper cable, right? So we're going to push it in like this, and it will snap in place, right? So think of how the electrical current will run through the circuit now, right? It'll go through this red wire, it'll go into the red rail, through this jumper cable, into row 5, and then into the button, right? Where is it going to come out? It's either going to connect diagonal, yes. And if this button is shorted between the 2, you can also use this row right here. See that? Because these 2 are connected together. Some buttons don't do that, some buttons do. It's really weird. It just depends on where you get it.
Yeah.
So just always assume it's connected, because if you don't, then if you use a button that, you know.
Yeah, just assume it's connected. If you're unsure, just read the spec sheet.
Yeah. Some buttons don't have spec sheets.
Yeah.
So you can also test it with a multimeter.
Yeah.
So the next thing we're going to do is we are going to go ahead and connect this button to a resistor. Now remember the thing that Sam said, no, you don't want to connect like the 2 ends of the resistor on the same row, because that will make a short, and shorts are not good most of the time. So what I'm going to do is I'm going to connect the resistor from the diagonal of the button to a different row. The important thing to note is it's a different row, all right? So from this row to this row. And I'm going to just press it in. Is it connected?
So, yeah, that's good.
Okay. So let's go over this again. Where is the current going to go? It comes from my power supply, goes into the board, goes through this white wire, into this button, crosses it diagonally once we press the button, into this resistor on row 7, crosses past the resistor into row 10, and we're stuck here now. So, yes. Oh, so again, how do we get back to ground? What components do we still need to put in this breadboard to get this point back to ground? Well, we need an LED, right? And then a jumper wire. So I'm going to take my LED, and remember, it goes from positive to minus, right? So the positive is a longer leg. I'm going to put this in row 10, and then I'm going to connect this from row 10 to row 11. Okay. So now it looks like this, right? If I just feed through this current, it goes from here to the white wire, through the button, through the resistor, and now through the LED. Where is the current after the LED? What row is it on?
11.
Row 11, right? So I connected it from row 10 to row 11. So what do I need to do to connect the circuit to ground? Good. Yes, exactly. So ground will be at the blue strip. So we just connected from row 11 all the way back to ground. Okay? So let's do this one last time. Where's the current going to go? From my power supply to the red rail, through this white wire, into the button. Now, if I don't press the button, it's just going to stop there, right? Because the button connects things. If I press the button, it's going to go through this resistor, into this LED, through the LED, into the brown wire, from the brown wire going back to ground, and then powering the LED, hopefully. All right? I can see some of you guys already did it. So we're going to go ahead and turn our power supply on through one layer of safety, 2 layers of safety, and we can see that the LED doesn't actually turn on yet until we press the button. All right? That work for you guys? Yeah, it's bright. I'm telling you.
I remember there was a time when I was using a 330 ohm resistor on an LED, and I was in Chris's Switch deal, and they were like, "Why are you using a 330? Use 1000K." And I'm like, "Well, I like them bright." And he's like, "Well, you're like limiting the life of your LED by quite a bit." And I'm like, I don't care.
It's cheap. If LEDs were like $100 each, I would be concerned. But like they're like barely a cent.
Finishing my circuits at 10 o'clock at night, I want to see those LEDs burn my eyeballs before I go to sleep, so I can know that it works. Yeah.
Generally, there are 2 ways of making your LEDs dimmer, right? One obvious way is using a higher resistance, because that'll decrease the number of currents. Remember last time we talked about how resistance and current are inversely proportional, right? So higher resistance, lower current. The other way is using what's called PWM, pulse width modulation. If you don't know what that is, it's okay. You don't need to know it yet. Yeah. Basically, you're faking a lower voltage. So for the most part, right, I can't change this voltage from 5 volts to anything else. But if I modulate or change the input source into a square wave, it basically tricks the LED into thinking it's being powered with a lower voltage. And if we have a lower voltage, then what happens to the current? Doesn't go up. It decreases, right? Because voltage and current are directly proportional to each other. Does that make sense?
And that is due to what law?
What law? Ohm's law! Yeah, we're getting it, guys. Okay, so we've got a blinking LED, which is great. Now, I want to implement a safety switch because I really don't trust my electronics. So we're going to move on to talk about SPDT switches. Where are they? Okay. Now, so these SPDT switches, there are a few kinds of switches out there. You have these ones, which I think I bought because they're breadboard friendly. Or you can get DIP switches, which I absolutely hate because they're like so tiny and my fat fingers can't get a hold of them.
And then there's also, we call them like through-hole prongs.
Yeah.
That's like the stuff you see on like more industrial stuff. I call them boat switches because you see them on boats pretty often.
Yeah, usually on PCBs.
Yeah, well, I mean, big ones, like for arcade machines too, like those big
Oh yeah,
look through hole stuff.
yeah. Like
Cars have them.
very few switches good for breadboards.
No, yeah, I mean, well, it's like there's a different thing for everything.
Yeah.
So.
Okay, turn off our power supply. We're gonna attach a switch right before this button. So let's go ahead and discuss how switches work. We use the same paper that I've been using all day. So again, switches have 3 terminals. I'm just gonna draw them like this. Okay, that's a really bad thing. I'm gonna draw them like lines, okay? That's what the switch looks like. And it has 2 configurations. It can either be on the left or it can be on the right, okay? If the switch is on the left, then these 2 pins are connected together, okay? And if the switch is moved to the right, then these 2 pins are connected together. All right. So depending on where you position your switch, you can redirect the flow of current. All right. Which you can tell by these 2 drawings that there's 1 pin in common. Which one is it? The middle one, right? So the middle pin will always be connected to something, right? For a lot of times, actually, for the design of the circuit, when you have like 3 different prongs, actually, I think this is SPDT.
Yeah.
This is not SPST, this is SPDT, which means single pole, double throw. So there's 1 input, 2 outputs. Right?
Yeah. Yes.
Yeah, okay.
Because if it's single pole thing, single throw, that means that you're just gonna have 2 connections and 1 is
Single pole, single throw is the button.
Right.
Yeah. So single pole, single throw, which means there's only 1 way of connecting them together. There's 1 input and 1 output, right? Single pole, single throw. In this button, usually, or in this switch, usually in the circuit diagram, you'll see them drawn like this. Okay. And you'll see that you have a center pin which correlates to, let's say if I number these A, B, and C. This center one will be B, and then you have A and C right here. And this rotates between A and C. So basically, whichever pin it switches to, that's the one. That's where it's going to connect, right? Now, for your circuit, we either just want this to be like on or off, right? So you don't need both pins. You can just like put an X on one of them. Basically, you're not going to use one. That's just going to be a no connect. Whenever you put an X, whether it's in a simulation or a PCB design that just says no connect.
That's the Altium no connect.
Yeah, it's a dead end.
The Altium no connect.
So if this is your 5 volts power supply, and this is the rest of the circuit, then basically all you have to do is just connect this to 5 volts, B to 5 volts, right? A to the rest of the circuit, and then deal with just leave it alone.
C, whatever.
Yeah.
Or you can do the other way. You can use C for the.
Yeah, or you can just put it on C.
Yeah, you put it C.
But the most important part is you get the center one correct, because the center one's going to be the same either case.
Well, I guess explain what would happen if you try to put 5 volt on either A or C. Right? Because what's going to happen is if you try to connect, there's those 2 pins, the 2 outer pins are never going to be connected.
Yeah.
With each other.
Yeah. You cannot connect A to C.
Physically connect.
That's illegal.
Right. It's illegal. Yeah. Unless it's not switch anymore, right?
Yeah.
So, yeah.
Okay. So what we're going to do is we're going to connect 5 volts to the center of the DIP switch. And then, A and C aren't labeled. They can be like either end. You just call them like the end of the switch. So what we're going to do is we're going to get back our breadboard. And we're going to modify the circuit so that we include an SPDT switch.
These are not polarized.
Not polarized, so they don't matter. The direction doesn't matter. Okay, so remember, the middle pin has to be 5 volts, and one of the end pin has to be connected to the rest of the circuit. So I'm going to just put this switch right here. Okay. Oh, I like this fit. It's like okay. So from the diagram, you can see that the right end of the switch is connected on the same row as the button, which means it's going to be conductive. And then we can take the middle jumper wire and put it in the center, right?
The center pin of the switch.
Center pin of the switch. So in this case, the switch is going to have 2 modes, or 2 states as we call it. If it's in the left state, what do you think is going to happen? Right. Where does current try to flow?
Which one's left?
Oh, sorry.
So he said no flow, because I'm like.
Oh, so in this picture.
Yeah, in this picture.
Yeah, in
right.
this picture. Yeah. In this picture, you're right, because the current's going to try to flow into this direction, which this pin on the left here, in what you're seeing, doesn't have any connection. So that's just going to be a dead end.
Right.
Okay, what happens if I flip the switch to the right? What happens then? Right, so the current's going to flow through the switch into the button, into the resistor, into the LED, into the jumper wire, and into ground. Yeah. Correct, yes. Because that's 5 volts.
One way that a lot of guys is like, well, how do you demonstrate, how do you remember that? Is to really kind of remember like what this component is, right? Because it's not that big, there can't be that much going on in it. So the biggest deal that I try to remember is that little throttle thing that's sitting on the top there, what it's connected to is literally just a metal plate. And when you slide it over, it's essentially making contact with 2 other little plates inside of it. It's just creating that short just by doing it. Right? It's just a metal plate. So wherever the metal plate, it's just the right size to make it so that only 2 of them can be connected at once. You can, with shitty switches, okay, you can kind of go in between that and bridge all 3 of them if it's not quite cut right? And I've actually gotten switches to do that. And the problem with that is that then if you have a really bad switch like that, you're connecting all 3 states together, and that can actually lead to some pretty problematic issues, right? Like my power supply will say like, oh, it's like grounded, it's like shut off, right? Like something's power's flowing somewhere, it's infinite loop kind of thing, it's doing a bunch of different stuff. You don't want that. So these kind of components do have problems, right? And that is a problem that comes from the physical design of the switch. Same with any of these kinds of components, they all have physical problems. That's like the best way that I can actually remember. Yeah, you don't even remember like that set of things.
Good question. All these components have like that negligible, I can't say the word.
Negligible resistance?
Yeah, resistance, right?
In real life, no. In this deal, in our funny little world, yes, right? But the resistors, those components, all that kind of stuff, they do.
Everything has resistance,
Everything
even the
has
wires,
resistance.
even the jumper wires.
Now, in our case, for lighting up a dumb little LED, yeah, no, it's negligible. Okay, but in IRL, when you're designing stuff like me and Chris for people kind of thing, no, it's not negligible. You do need to consider it, right? Because especially if you're picking components that need to be placed into stuff, right? Especially for, he likes SMD stuff, so which means surface mounted design, meaning that the LEDs are not going through a hole; they are like physically sitting on.
It's what you see on the PCBs.
Chip. Yeah, that's called surface mounted design. That is especially important, right? Because now you are even limiting the connection like even more. So it's like trace sizes, wires, all that kind of stuff. Yes, absolutely. Resistance does matter. In the funny theoretical world, no, it doesn't, because a resistor means that it has a resistance of. What does the wire in my funny little world have? The resistance of 0. Nothing. It's great.
Yeah.
Now there are theoretical ways to actually get a resistor to go to 0 in real life. Okay?
There are 0 ohm resistors too.
Yes, but that's like more of like a physics thing. There is a way to do it. You can dip the whole circuit in like a cooling solution, and what you'll do is for the copper in that wire, you'll reach what's called superconductivity state. And there's a way to do that, but it is not cheap. It's not easy, and it's probably not suggested for everyone. So, because I don't think any of you guys have like liquid nitrogen systems. So, but that is actually what I research is material science and that kind of deal for conductivity states and stuff like that. So, getting close.
TLDR, don't worry about it.
Yeah, TLDR.
All right, let's test the circuit now after that talk. So when I turn the circuit on, I shouldn't see, actually, let's call this a safety switch. If my safety switch is switched in the off position, I shouldn't see anything happen when I press the button, right? Because, current doesn't flow there. But as soon as I flick the safety switch off or on or whatever, I can press the button and see the LED turn on. You guys have that? Expected behavior?
Cool, great.
All right, awesome.
But you guys are a good group.
Yeah, no, you guys are awesome. Yeah.
No problems.
You guys want to move on to digital logic components now?
Yes.
Okay. So, again, how many of you guys were at last week's workshop? Okay, so I don't have to go too far back. Okay, let's talk about datasheets. Okay. Datasheets are an engineer's best friend, although many students kind of ignore them because they think it's, wow, it's a lot of words, I don't know how to read this. You know, it's the most useful thing you can imagine when researching what chip to use or what specialized component for a PCB. In this case, we're just going to talk about like regular gates, right? Regular AND gates. Now remember that, you know, these components here have like one of each gates, and we're gonna just find the 74LS08. It may be a little hard to like see which one it is because it's written on the top.
Yeah, if you guys are having trouble reading the little stuff on the top there,
Yeah.
just talk out this out.
Shine it at a light because it's easier.
Or I'll show you.
Yes. Okay. So I don't know if you can see this on the camera. You probably can't, but it says 74LS08N.
Well, it's the bottom number, right? So it
Yeah.
says SN74LSO8.
The most important thing is the 74LS and the number after it, right? There's a lot of variants like HCLS08 or the HC series. It just means like different ways of making it. I know one of the names is for the military grade, one's hospital grade.
The general 72 or 7408. That is the chip.
Yeah, very general. So, you know, these chips will work. And there was a hospital grade one too. Yeah, it's crazy. But this is like, this is called consumer grade, which is like the regular one. It's just like some of them are more expensive just because they have like extra cent of protection on it.
Right,
ESD
higher
protection.
tolerancy, longer lifetime, better parts. In this field, in electronics, and I think I've said this every time I'm in one of these, you get what you pay for.
Yeah.
That's how it works.
Yeah.
So pay more per component, you're gonna get better stuff.
Yeah.
So
These chips I bought for like about 50 cents to 54 cents.
it's a consumer.
It's not super great, but also not super
Consumer grade.
consumer. Yeah, what he said. They're for consumers like us who are just learning, right?
If you buy the military stuff, it's like $10 per chip.
Oh, yeah.
almost.
Oh yeah.
But that stuff, that shit will survive crash. Yeah, no,
Yeah.
it's good stuff.
Okay, let's talk about minimum configuration. Now, this is an AND gate. Does anyone know what an AND gate does? Can you tell me? Yes,
Okay,
two
yeah.
inputs.
What do you think it does with those two things?
Uses an output
Right.
One output.
Based on what?
to positive.
Sure, yeah. So,
So-
we call that logic.
Yeah.
Yeah.
In logic, we just use ones or zeros. So, you know, one will be your
High,
positive.
low, positive, negative, whatever.
Yeah. It's all the same, but in this case, we're just working with ones or zeros. So in this case, the rule is if both the inputs are a 1, then the output will be a 1. Otherwise, it's a 0, right?
That's for AND.
Yeah, that's what this truth table says actually. So we're going to analyze this a little bit. So this truth table basically gives us an A and a B as an input. So if I make an AND gate right here, and I call this input A and input B, and this is Y, right? Kind of what our circuit diagram says here. We can see on the function table that we have combinations of all possible inputs, right? And in this case, it would be low and high is what they're saying it, right? Sorry about the camera quality, it kind of sucks, but in this case, we have low, 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 high, low, high, low, low, and then high, high, high. So you're seeing like the only time in which the output is high is if both inputs are high, right? Cool, so we figured out the logic part. Now we have to move into circuits. In circuits, in order to power one of these chips, you need to give it a minimum configuration, which means you just gotta give it external power. In any of these chips, you have a VCC pin and a ground pin, right? And usually the way you look at it is, they don't have it mapped here, but usually there's a semicircle right here. And you count the chip's pins like this. There's 1, 2, 3, 4, 5, 6, 7, like the pin numbers. And when you get to 7, you go around to 8. So we have 8, 9, 10, 11, 12, 13, 14, yada, yada, yada.
Yeah, it's different. Just read the data sheet.
Yeah,
Different
read the
guys
data
count it differently. Sometimes the pins start at the top for one, sometimes they don't. Load up some really expensive stuff because sometimes the stuff is not specified.
Yeah.
So, that's really, really, really important.
So read the data sheet.
Read the data sheet.
Any chip you use, please read the data sheet.
Most of these 47 whatevers, okay, pretty much always have a VCC on the opposite end of the ground, right? 'Cause that's
Not for 555.
like the 07 or the
Oh,
074 or whatever.
They're all in what's
They-
called
they are-
family, right?
They are a family,
Yeah.
a chip family, whatever the case may be, and they all pretty much exert that exact same.
Yep.
So,
So in this case, when working with these chips, again, always the minimum configure out. It's an important word. I really like it. I got it from Evan. So minimum configuration.
oh yeah, that's right. Yeah, minimum config.
For different chips, it's different. Like if you're working with a microcontroller, it's different. But in our case, we're just working with a 74LS. Okay. All right. So in this case, this is a quad 2-input AND gate, which just means it has a bunch of these 2-input AND gates, and there's 4 of them. Right? That's how you just analyze. It's pretty simple actually. There's 4 AND gates inside this one chip, which is useful because if you want to use multiple AND gates in your circuit, you can just use it on this chip.
A lot of real estate.
Yeah, real estate is fresh. So in this case, one AND gate is on pins 1, 2, and 3. So you can say, if I want to connect something to this chip right here and have it be an AND gate, I'm going to connect the inputs to 1 and 2. Let's call this input. And I'm going to say 3 is the output. So in circuitry, basically I'm trying to say, I'm going to pass a high signal, or 5 volts, into both the inputs and see what the output is, and 5 volt or 0, right? Because in this case, we're going to connect this to our breadboard later on, and we need either get 5 volts or 0 volts. And the output will be either 5 volts or 0 volts usually.
Yeah.
Check the data sheets.
Yeah.
It'll be different. So, this is how it generally works. And you can do the same thing for pins 4 to 6, 8 to 10, and 11 to 13, right? So 4 gates.
Yep.
So let's take a look at the other things in this data sheet. I'm not sure how clear the wording will be for the other ones. I'll try. So usually on the second page, that's why I forgot my GoPro would have been good.
Not usually ever. Data sheets are almost always different. Depending on manufacturer. There is no standard for that, unfortunately.
Yeah.
That is,
They mostly have the same information.
yeah, they will, but it's just in different places and different deal.
Yes.
There is a skill that you learn as an engineer that's called data sheet skimming. That is a skill to understand the stuff that you need really quick. Not spending too much time.
Sam and I go through many chips when building PCBs, and through the many chips, all we do when we leave the data sheet is what are the power conditions, what are the pinouts,
Yep.
Any structural
It's an
malfunctions.
analog or PWM, but I don't really have to worry about that as
Correct.
much anymore. Based on my new job.
Yes.
There's just little things. Operation, temperature.
You don't really have to care about that
I mean,
unless you're cooking them.
Unless you're, I don't know where you're at, but if you're in a place that's like 150 degrees centigrade, then
If you're in a volcano, be concerned.
sorry, your chip's not going to work.
Yeah.
So, other than that, so
The other concern about that actually is if you're doing SMD soldering with these chips,
absolutely.
you want to make sure that you're not blasting a heat gun to it to melt the solder and it's destroying the chips.
Right,
internally.
yeah, I didn't even think about that.
I've done it before. That's
Yes.
why. That's why I'm warning you.
I did not think about that.
So-
yeah.
So this is from Fairchild Semiconductor. That's like a company. They usually have the electrical components on the second page. So you have a bunch of charts here. The main important part is to think of supply voltage. I'm going to read it to you because I don't think you can see it. But this says 4.75 minimum voltage and 5 nominal voltage. And max is 5.25. So basically you can supply this chip with 4.75 volts to 5.25 volts.
If you go above it, you probably get blown up.
Yeah. And if you go below it, you're not going to power it up. Next thing is high level input voltage, low level input voltage. These don't really matter unless you want the application. Pretty much what the current might be interesting if you're trying to power some
You're trying to power
module.
something. Yeah,
out
if
of
you
a-
don't think your LED's gonna be powered off of it, then you can look at that. But
Yeah.
generally, that's not really how to do it.
Yeah.
That's what it is.
Yeah, okay. So same thing, you can look at the electrical characteristics of it, but nothing's really interesting here. I'm going to talk about switching characteristics. Unless you're doing actual logic
Timing,
stuff,
yeah.
timing, propagation delay.
Yeah.
Unless you're
Critical
doing
path
that,
calculations,
don't worry
stuff
about
like
it.
that, don't worry about
Okay.
You're not gonna be doing something like that with this anyway. So.
If you want to model this in CAD, I would say Y, because there's STLs out there. But you have like the dimensions of this stuff as well.
No, hey, I'm making my own footprints now. I'm not supposed to say anything.
Okay.
That's
Sam's making his own
that's
footprints.
useful.
If
That
you
is
want,
useful.
yeah, so footprints in PCB design is like kind of a like
Thing that
picture.
sits on. Yeah, and then courtyards is how much space it takes, and then the side. Look, if you want to impress your boss and make like a really pretty CAD, then it's what I've been working on for like the past year. Now pay me. Kind of thing. Then that's like pretty much how you would do it. You spend the time to make good CAD models. So anyway.
From very common components, if you go on like mouse or electronics, they'll have them.
But special stuff sometimes the
Like
CADs
specialized
don't have
chips
everything.
too.
Yeah.
So. All right, so structural stuff on like all the pages, here too. So most of the important information is on the first 2 pages. Yeah, it's no fun. Okay. Now, before we get into actually building this on a circuit, I have to go over a very important topic that I unfortunately did not learn until like my 2nd semester here at college, or too deep into my career, I would say, because I've been working on this for a long time. Topic is pull-up and pull-down resistors. Okay. Oh, my pen broke.
You've seen it, you've heard it, you've probably done it before, maybe. It's an important concept for us to kind of understand like why certain things are probably not. It's not your fault, right? It's just something that you need to understand.
Yeah. So the big question is, how are we going to feed our inputs into our chips? Because we can't just connect, well, we can't just connect 5 volts and 0 volts to them, but oftentimes they're connected to a button because, user input, right? So user input is kind of like wild, because if we say, okay, I have my chip here, I'm going to simplify this thing by saying it's just going to be 2 inputs and an output, and it's an AND gate. This is not a block, it's just a logic block, because I'm just simulating a circuit, okay? So if I connect 5 volts, or if I connect a switch, like an SPDT switch, like a button to it, right? And I put like 5 volts at the entrance. What's going to happen is, if the switch is closed, right? If the switch is closed, then current's going to flow through into the chip. That's normal. But what happens when I open the switch? It's an open circuit, yes. But what does the AND gate read?
0.
Does it read low?
What do you think?
Remember that the chip is being powered by like external voltage.
Right. So what did you say?
There's still current, so it's going to be.
No, not exactly. Not exactly. You're getting close there. Yeah.
Is it floating?
Floating is a good word. So
Yeah,
we
like
don't know what the state is. It can be low, it can be high. It's a gray area. So you're uncertain.
Because the thing is that in the fancy world of electronics, you have situations where external stuff like the power and stuff like that can actually affect states of things, because you have magnetism, you have a bunch of just stuff right, and especially in speakers, that is especially a big problem, right? So yeah, that's something you have to account for.
Yes.
Right, exactly. Interference, it happens all the time.
Yeah.
Is that noise?
Noise. That is the word I was looking for. Noise. Yes, that is a word we were looking for.
Exactly.
It is noise.
Yeah.
And what does that noise mean? Nothing, right? It's just garbage, right? But we want it to be zero. So how do we get rid of it?
Well, we've talked about this in the last lecture. Yes. We use a capacitor.
You could.
Yeah.
You could use that. Yeah. If you're a big brain, you want to clean up the signal and everything like that. Absolutely. Yeah, you could. Yes, you could. Yeah. What is it? What kind of resistor? Pull up, pull down.
Pull down. You got the right one. You got the right one first of all. Yes.
Pull down.
So in this case, it will be a pull down resistor. Now, really, what this means is pull up, it will go to 5 volts, and pull down will go to 0 volts or ground, right? And in this case, if we want to stabilize the signal after the switch has been released, we want to pull down the signal to ground, right? Because we want to tell the chip that, oh, I am having a ground now. So I'm going to connect this pin to ground, not directly through ground, right? Through a resistor.
Yeah, so basically the idea is that, why do you think we call it pull up, pull down? Right? Think about it. What is it doing to making sure, like when you mention your noise deal, what's happening in the noise situation? Where you just have noise and everything's floating around. Like a floating thing, kind of like what he was describing. It's a value that doesn't necessarily mean anything.
it's supposed to be 0, but it could be just a bunch of crap, right? Because, you know, you decide to run your massive subwoofer, you know, speaker wire right next to it, right? So it's going to completely destroy it. A pull up, pull down is physically pulling, right, the actual value down to where it's supposed to be, right? Whether it's 5 volts or 0 volts or 3.3 or whatever, it doesn't matter. You just want to keep it there, right? So by adding a resistor in line to your ground, it's not ground, right? Because you're not like, you know, sometimes ground can also be a problem too. But it's kind of like a barrier that kind of says, okay, yeah, like 100% this is 0, but it's protected. It's a protected ground, right? Like it's not like a harsh ground where you're just shoving the thing down into the ground kind of thing, right? So
adding the resistor kind of makes it approach 0.
Yeah, well, approach is kind of hard too because there's this whole idea behind like curves, linear stuff. But yes, that's a good way to put it. It's like an approach, right? Yeah, it's a very easy approach, right? Instead of just saying ground,
Go to 0.
yeah,
Fall off a cliff.
yeah,
Yeah.
die, right? So that kind of thing. So
Exactly. Okay, this was actually the easy one. Pulling down to 0 volts. But a lot of times for microcontrollers, they actually pull up better, right?
Well,
Some do.
the one that me and Chris had to use did not.
Yeah, no, that didn't like it. So if pulling down was pulling down the signal to 0 when the switch was open, what do you think a pull up resistor is? You're being pulling up to
Or,
1?
Yeah, the one value.
Yeah.
Sure. Yeah, absolutely. Your one
Yeah.
value. No, that's fine. Yeah, your one value, your 3.3, your 5, whatever it is, right? Your logical one, right? In this case, your physical one, right?
And you're gonna do it through a resistor as well?
Yeah.
And to 5 volts.
Yeah.
Okay.
Do you need like both resistors for both inputs?
Yes. Because generally, okay, I know what you're talking about, right? Because it's kind of like it's within the same deal and everything like that. Yes, you do, right? I mean, you don't have to, okay, but if you want to be thorough, which is something that is greatly appreciated by any boss or any person who hires you for this business, it's okay to add one more resistor. It's not going to hurt. Right?
Yeah.
So it's not going to hurt.
Yeah. So not too big of a resistor, it'll be like a open circuit.
Right.
Yeah. It's a bit careful. Moderation.
Moderation is smart.
Yeah.
Yes. So
what
no, but yes, it's okay.
Yeah. What happens here is if the switch is open, right, the AND signal gets a 5 volt signal from down there. When it's closed, then the current can pass through the switch, go to ground, and this will be at 0 volts. This node or electrical like junction is what determines what logic value the gate gets.
That's some kind of harder math there, so neither one of us expect you to kind of figure out what's going on there because that's kind of confusing to look at.
Just think of ones and zeros.
Yeah, it's just enforcement.
And the whole idea of this is just to make sure that you have solid signals all the way through. Again, no floating signals, no gray signals. Don't confuse your chip. It won't confuse you. All right, so now we understand that. We're going to construct a simple circuit using an AND gate. How much time do we have? Okay, we're going to construct a simple circuit using an AND gate and our LEDs, and I think this is actually the last one on my list. And then we can introduce some challenges for you to go and try this out in the lab yourself. All right? Okay, so again, if you don't have these data sheets, you can just look them up online. Just type the chip name into Google with the word datasheet after it. First things is the PDF. So pretty simple. What I'm going to do is I'm going to go ahead and start taking some components out. I want to have kind of 2 buttons into a IC chip. And so what I'm going to do is I'm going to put 2 buttons here. And you know, I'm going to do this using jumper cables, but Sam knows I'd like to do this. You can also use these cables. There's like automatic wire strippers in the room. You can make your circuit look really neat and with wires all the way down to the board. It's a whole skill, but I don't have time to like do it now though. Okay, so we're gonna have 2 colored buttons. We're gonna have a yellow button and a green button. Okay. right here. Usually goes across the bridge. And then I'm gonna put my chip inside of the board. Just gotta find the right one first. Gotta find the right one first. Gotta find the right one first. Here it is. Okay. So remember, the chips do have a direction, so be careful of where direction you put it. The best indicator is this semicircle right here, semicircle notch. Pin 1 is going to be like, yes.
In there so that they can see that sheet.
Yeah. So in this case, the semicircle is pointing to the left, which means pin 1 is going to be this pin right here. So in this case, right about here. Right. Now, based on the minimum configurations, what do we have to plug into the chip initially just to make sure it works? The first thing you gotta plug into the chip.
Your power, right? Yeah.
Power, right? VCC and? Ground, yes, good. So we're gonna plug into our breadboard. You can follow along if you want. And we're gonna go ahead and connect power and ground to it. And I think at this time I'm gonna go ahead and cut some wire just to showcase you what you can do in the lab. Why this is a brand new roll of wire. Okay. So what I like to do, I'm just gonna toss this aside for a second. I have a automatic wire cutter. Now the lab also has some automatic wire cutters, but they're not that great. And you guys can use the DuPont connectors. So I'm gonna go ahead and cut this off like this. And so you'll see that this is a solid core 22 gauge wire. It's like solid, so there's no like wire whatever is on it, but it's a pretty good one for connecting your breadboard. Now I'm gonna teach you guys a technique that I use to connect them really well. If I want 5 volts, and remember that 5 volts is going to be.
What's the name of the chip again?
Huh?
What's the name of the chip?
74LS08. This is a quad 2 input AND gate, right? So the behavior I'm going to go for is I have to press 2 buttons at the same time to get the LED to light up, because that's logic, right? Okay. Yeah. So both of them have to have high signals for the output to be high, because that's how an AND gate works, right?
And logic.
And logic, yes.
There is this kind of thing can be found in programming languages and all sorts of stuff.
Yes. You want to reprogram it on first week?
Yes.
First week. Okay. So VCC is going to be pin 14, which means that this goes to
The same line as that first.
That is correct. So what I'd like to do to make this like really nice is I plug it in first, and apparently it's impossible to plug into this breadboard. Different breadboards have different qualities, I guess. Yeah.
You said that the little thingy it goes this way, right?
The notch, you just is as long as you understand. Yeah. So like in his case, the notch is facing the button. So
Yeah. It just make sure you know where it is. So I mean, you can use, if you're using these wires, they're not very like strong, so you can use the DuPont connectors to kind of like loosen it up a little bit.
So the notch should, if there is a specific direction, the notch should face so as long as you understand the notch is relativistic. So the notch indicates what his want. So it kind of tells us right now. But in his case, if you're following him directly, then in this case, the notch is facing the line.
Okay, so I've got some wire connected to the board, and what I like to do is I kind of like to, I have this little muscle memory like in my hand that I just go, you count like 3 squares out, and then you cut from like where you want it to land, so like 1, 2, 3, like here. Basically, we're trying to get the perfect wire here. And then you can cut it again. Now I'm going to cut it using the, if you have an automatic wire stripper like this, it cuts it in like exact length, so you don't have to worry about it. So I just plug it in like this. It's a little bit short, but it's okay. So most of you guys are going to use, there's some of these tools inside the room as well. These are manual wire strippers. So what you're going to do is you're going to feed the wire into whichever gauge it is. Actually, I think these are 16 gauge, right? 14? It's 22. It's 22 gauge. Okay. AWG is adjustable.
It's just there's gauge, and the gauge is basically the thickness of the wire.
Yeah.
So the lower the gauge, the bigger it is.
Yeah, so I'm going to plug this into here, and then plug this into the breadboard.
Yeah, so he's just doing it, you guys can just use the jumpers.
Yeah.
Just use the jumpers.
That's, the
Honestly,
first one on the
he's
top,
just showing
right?
off.
Yes.
Just do the jumpers.
Number 8.
So this is going to be a number 18 if you're following me exactly, right? And I'm just going to be lazy and go straight to ground. So ground is going to be this pin on the bottom right corner, and I'm going to put it all the way over here.
If you try to put it on this thing, because I know it's enticing, because even in my head,
It's closer.
I like the intrusive thoughts and thought like, oh, you should plug it in over here. That's perfectly fine, but there's one thing you need to do before you do that, like to turn everything on and everything like that. What is the one thing that you need to do if you're going to treat this as a ground? Right, you need to jump it, right? So you need to jump it to ground, because that is something that is called common ground. In my final project, for the class that I took with him, it wasn't working because I forgot that one wire. And everything was acting wrong because there was literally 2 separate grounds for this entire circuit and they had to be the same. That's why they call it common ground, because it's shared amongst everything inside of that circuit. If it doesn't, it's not gonna happen.
So how would you do that to jump?
Just jump them. So blue
So,
to blue from
yeah.
one side to the other. Yeah.
Okay.
Yep.
It's a very common thing you need to do
Yeah,
too.
in fact, most of my breadboards, I think, already just have them on there. Yeah, they're just like a little thing that's just kind of pressed on that just does that.
So you go from blue here to blue over here.
Blue over there. Yep.
Okay. And then both the blue rails will now be connected.
Inhibit the same ground.
Yeah.
So you have
Correct.
to do the same thing for the regular.
Only if you're powering stuff from that.
If you want both ones to be red, you can do that too.
Absolutely. Yeah, if you want them both to be powered, it's fine. Yeah, but if you don't, who cares?
Okay. So in this case, I have my output already configured. So this gets power and this gets ground, which means the chip is now actively working.
Yep. Or well, when it turns on.
Yeah, well, it turns on. So what I'm going to do now, and I'm actually going to put this common ground here just so we can take a look at what happens next. I'm going to do my output first because I think it is easier to do. I'm going to connect my LED, and remember the LED needs a resistor, right? Else, bad things will happen. I'm going to connect it to the output of this chip. Now, if we take a look at the data sheet, the output is on pin 3. So this third pin from the left here on the bottom row is where I'm going to initially connect my LED to. So from the positive end to the negative end, I'm going to bend my LED so it goes to this wire right here. Okay. Like this.
Why there is resistance? Why is that
LED, yes. So the LED is now in a separate row, which means it's not conductive with the, with anything else. So this row is reserved for the end of the LED. What I'm going to do next is I'm going to place my resistor, my 330 ohm resistor, wherever it went. I'm going to go ahead and cut this one.
What are you putting the LED on? Which one?
Pin 3 of the IC.
For the LED, the short or the goes to the
Positive is long. Long is positive, short is negative.
Positive on the that's right.
Yeah, long is to 3. Yep.
Yes.
Okay.
Yes.
Well, let's see.
Pin 2 is an input, right? So if we look at the data sheet, pin 2 is an input right here.
So is that where the positive is?
No, we're not doing inputs just yet. Those, if you're getting buttons, those buttons are where it's going to go.
or the buttons are input.
Yes.
Buttons are the inputs, yes. Okay, so we're dealing with outputs right now, in which we're going to place the output as an LED from the IC to a separate row, and then we're going to go from a separate row to ground, right? So I'm going to cut my resistor and place my resistor into this slot right here.
Where does the negative one go for, or
For what?
the LED?
The negative one just goes outside the chip, right? It's in a separate row, not included in the chip.
And you're connecting the resistor to the same row as the positive? Yeah.
Say that one more time.
You're connecting the resistor in the same row as the positive as the LED?
You are connecting the
330.
resistor in the same as the positive row of the LED. Yes, you can do that. But that would have to go to ground if you're going to do that. Okay. Yes, that is perfectly fine.
Okay. So we've got our output
Or no, hang
configured.
on. No, I'm sorry. No. I'm sorry. It's the resistor is going to go to the negative. Yep. Remember that cannot share, right? That resistor cannot share any pins with the chip there, right? Like that resistor and the negative lead, because
Those other two pins that are right after, they're the 1, 2, and 3. We need them. Those are like right, correct. And we don't want to just send that to inputs.
And you're just connecting the resistor straight to ground?
Yeah.
And
Because that will power the LED once it's turned on.
Yep, the resistor, it doesn't matter if it's before or behind. As long as it's in, it's good. So if you be behind the resistor thing, it's going to do the same thing. Because, you know, power electronics, whatever, all instantaneous, how that works, right?
Yeah. Okay.
Oh, it could be after the LED.
It can, absolutely. Yeah. Very interesting concept, but yeah, it actually doesn't matter.
So we are going to go ahead and do the inputs now. We are running out of time for the lab, so I'm just going to rush through this a little bit quickly. I like using pull down resistors.
Yeah.
Pull down.
Well, this would be.
So when we press the button, we want it to turn on,
Right.
which means this should be a pull down.
Yeah, it should be.
Okay.
Because it's positive by inheritance.
Right. So I'm going to use a 10K ohm, or you can use 1 kilo ohm. I think for buttons, usually it's 1 kilo ohm, so I'm going to use 1 kilo ohm resistors. It really doesn't matter, just to make sure it's not too big or too small. 1 kilo ohm to 10 kilo ohm is generally a good range. So I'm going to pull two 1 kilo ohm resistors out of this pack here, and I'm going to cut them to size using my component gauge. I love this thing.
Yeah, I got like 3 of them and I just never use them. So just forget.
I carry one in my backpack all the time.
It's pretty easy. You just say JLC PCBs. So that's funny.
Yeah. Make a PCB out of this.
You know, I bought a big replacement.
Oh, really? Oh, wow.
I'm going to start building it.
Oh, wow, cool. Okay, so you remember that the button is connected diagonally? So we're going to place the pull down resistor after it. So if we think that the top of the button is before and the bottom of the button is after, I'm going to place the resistor from the after pin to ground.
This is our pull
Down.
How do you think it is? Is it a pull up or a pull down? Pull down. Pull down. That's right. And why are we doing a pull down? Oh, you need help. Oh, yeah. Okay. Well, you point it down. So
Well, why do we need a pull down? Let's answer that
why-
question.
Yeah. Why do we need a pull down? To lower
To lower stop it from being confused, right? To make sure that when the button's not pressed, it knows that it's 0.
To both switches?
Yes, to both switches. Because we're going to make a circuit that only turns on the LED when both buttons are pressed. And we're going to put it here. And put it here.
Oh, so the button is like a beacon.
Buttons at the beginning of the circuit, actually. Because you want the buttons to be the input. So we put this in here like this. Okay, so now we've got the pull down resistors after the switch. We have to connect the switch to the inputs of the AND gate. And I will go ahead and use some wires for this. So input 1 is going to be a blue color, and it has to go after the resistor. So it's going to be here, and this will go to pin 1 of the IC. Right, so pin 1 of the IC is right about here. Okay? Because pin 1, again, is the input. So from the data sheet, pin 1 is the input. And then we just simply use another wire to go from the second button. Actually, I placed this in the wrong line.
Oh, Chris, dude, this is interesting. This
Yeah.
Kid, okay, I'm sorry. What did you say? Nathan did something kind of interesting. So you're supposed to give power and ground to the chip, but you can technically create an AND logic with just buttons.
Uh-huh.
2 of them.
Yeah.
Do that.
Yeah.
On accident.
In series.
Yeah, you put them in series.
Yeah.
Yes. He made it.
Yeah.
So his exhibits it because he put them in series and created an answer. And so if so technically that is an AND.
Okay, so we're going to connect the input to the second button and connect it to pin 2, which is another input. So now our circuit looks like this, right? The output of each button goes into the IC, but also through a resistor to ground, right? So now we've configured this sort of connection here from the output to the chip and then the output to ground all we need is the input. And we can see that the input here for a pull-down resistor is at 5 volts. So we're going to connect the inputs to 5 volts each. Remember, it connects diagonally, so it's going to be from row 5 to VCC. Oh. And row 10 to VCC.
Yeah, you guys think this circuit's big, so you just wait.
Oh, it gets bigger.
Yeah.
It gets bigger.
Wait.
Okay, so this is what the circuit looks like. Again, we'll go over this a little bit, well, I'll retrace my steps, do a little summary, and then you guys can focus on building for the rest, or just tinkering around. So we have minimum configurations. In order for this chip to work, we need it to connect to 5 volts, and we need to connect to ground, right? Even if I can connect the ground to over here because I have common grounded already. Okay, so our inputs are going to be 2 buttons. Again, these will need pull down resistors such that when it's not connected to 5 volts, when we don't press the button, the signal gets pulled to ground, so the IC knows it's a 0 or a low or a negative or no or false.
Yeah.
There's like a lot of different things. Okay, so the buttons get pulled up to 5 volts initially because that's where we're coming from. So these go to 5 volts. The buttons connected diagonally, so it connects the 5 volts to this blue wire here, which connects itself to the IC. Remember, for the electrical configurations in this data sheet, that it likes anywhere from 4.75 to 5.25 of supply voltage. So in this case, when we press the button, it's going to go into the IC, and then it's going to go ahead and detect the inputs from both these buttons, the blue one from button 1, the green one from button 2. Now, if these buttons are pressed at the same time, because it's an AND gate logic, the output, pin 3, will feed itself into this LED and then feed into ground through this resistor down here. So we're going to go ahead and turn on our power supply. Basically, what this logic says is if we press one button, nothing will happen. If we press the other button, nothing will happen. And if we press both buttons at the same time, the LED will turn on. Fun, huh? Okay, so now we've established that logic. You guys can go ahead and try to build this on your own and see what happens. For Zoom, I will pause the recording so you can continue building, but for the people live, I'm going to go ahead and go over some troubleshooting tips now. You're back, Zoom recording. Okay, so we are going to go over some challenges that we are going to build inside the lab. I know we only have 30 minutes, but I think most of you guys already understand how to build a simple circuit, so I think this is a good opportunity to branch out and
Are you posting these slides?
yeah, yes, but you can take a picture of it too. Okay, challenge 1 is an LED driver. This is a really easy circuit. We've done this before too, and this is going to be just a simple turning LEDs on using a power source. So you don't have to use a 9-volt battery, you can use a 5-volt battery too. But the real challenge here is, we've done this already, adding another LED is fine, but what if you add 4 LEDs, right? If you do 4 LEDs in series, what do you think will happen?
It gets dimmer.
It gets dimmer until it will turn on, right? And why won't it turn on? Not the current, actually. Not the current. It's the voltage.
Right, your potential is lost.
Yes. Because, remember how I said every LED takes around 2.7 volts to turn on? If you have 4, you have 2.7 times 4, which is like more than a 9-volt battery. So it doesn't have enough like turn on voltage. It doesn't have ability to turn on all 4.
But as a result, your current drops, right?
Yeah.
You will actually experience something called a voltage drop, and your current will actually spike, right? You might twist it.
Yeah, that's right. So that's the first challenge. Second one is also really easy. This is called opposite input. You're going to design a circuit that has one input, which is a button, and one output, which is the LED. And pretty much it's not just a direct connection, but you have to just do, when the button is not pressed, the LED turns on, and when the button is pressed, the LED turns on. Pretty simple circuit, but here are some just guiding questions to get you to the answer. There are a lot of ways to do this, actually. You don't even have to use gates.
The chip. You can use something.
Do we have to use gates?
You don't have to use gates.
No, you can do it without.
You can do it with
It's
whatever.
possible. Yeah.
Okay, that's still an easy challenge. Should be able to do this in like 5 minutes. This is a fun one. A medium difficulty challenge 3, which is the ARM sequence. You're an electrician in a fictional military base, and your boss has requested you to build an arming sequence to launch a rocket. So you're going to design a circuit that has 4 inputs, which are color buttons, and 2 outputs, which are color LEDs. and it follows these rules. The red LED lights up when the yellow or red buttons are pressed. The green LED lights up when the green and yellow buttons are pressed at the same time. The red LED turns off when the red and black buttons are pressed at the same time, and the green LED should not light up when either the red or black buttons are pressed. Your challenge is to build a circuit that follows each of these rules, and then figure out the correct combination of inputs to turn on both green and red LEDs. That's when you launch the rocket.
We call state machines.
It's a state machine, yeah.
I hate them. I have grown to hate state machines.
Okay, that's challenge 3. Here are, challenge 3 again. Challenge 4, Blinky Learner. Now, for those of you who are here, I don't even know if there's anyone here from when we did the first Blinky Learner back in spring of 2021. But we did Blinky Learner. We're going to construct an LED blinking circuit using a 555 timer. I always do this as my fallback because this was one of the first real industrial circuits I built on a breadboard. I like the circuit in
Chris
general.
has a bit of an attachment to Blinky.
I love Blinky Learner. It's my baby. Okay. If you want to challenge yourself, this is Blinky Learner 2.
This is actually one of the things that this is actually a second lab for a second year course for us as a lab.
2300, you got to build this. So anyway, so yeah.
That is like the third or second lab, yeah.
You have all of the components you need in your kit to build this, by the way.
Dude, you guys are looking at me. Guys, we didn't even get this. We had to build this schematic in the lab.
I'm giving you the schematic.
We're being nice.
Gearson Lab, yeah.
Gerson, Ramos?
Yep, Mr. Ramos.
You know what? That guy's tougher than hell, but he teaches you so much, dude. I love Gearson. That guy's just, he's like our age. He's like 26. That guy's he writes, they're like hack tools that you plug into diesel engines to make them run faster or harder or whatever. It's like trick systems. It's actually pretty cool. He makes pretty good money from that. So he's a master's student here, and if you guys come here as an electrical engineer, I guarantee you're probably going to have Gearson for 2300. Hell. And you're going to suffer like the rest of us.
Yeah. If you want to prepare, you learn a lot. Yeah. So Blinky Learner 2 is the exact same circuit that we did for our soldering workshop in season 3. And so we're building it on a breadboard, and you have all the components you need in your kit to do it. So good luck.
Just barely.
Yeah. No, you have exactly. Sorry. Yes.
Yep, in that
So-
kit. You can build this.
All those lines are the connections that we have made?
Yeah.
Okay.
Correct.
I'm going to be honest with you. I've done it on just one of those singles.
Yeah.
It's hard.
I did it because I had to. Actually, I did it on 2, but you have to use 2. That's why you have 2 breadboards.
You can do it on one.
Yeah.
I've done it, but it's
The
not hard.
You have 4 ICs, 5 ICs, I think. No, because this has a reset circuit too.
Oh.
Yeah, it resets at 9.
Yeah, that's your reset.
Because you have 2 ICs and it's fine.
Yeah, to make it so that it counts back down to 0, you need actually another 2 chips.
Yeah.
Just to do that.
What are these two? You have the numbers right there, but these
So
three.
These are D flip flops. So they are 74LS47, I think. You have 2 of them in your kit.
Okay, and this one?
This one is a 74LS74, I think.
Oh.
Numbers are weird. But this has a 16-pin chip. It's a converter, a decoder for a 7-second display. It accepts 4-bit input and outputs the configurations to the 7-second.
That's fine.
Okay, so just to wrap it up, there are 5 challenges for you to build. If you want to send a video to one of us, you may earn a little prize or something. I really want to see if someone will send me a video of this because I've built this before.
I don't
It's
think I'm
hard.
gonna be able to build that.
It's hard. But you have everything in your kit, so no excuse.
Yeah, we build this at home. If you sent that to us, we need to be very interested.
All right. So you can now go to the lab and start building.
Yes, the slides are online.
and-
Chris, the slides are online, right?
No, I'm gonna post them on the Discord right now. I'm gonna post the slides on the Discord. You can work in the lab. The lab is open for you guys to enjoy. For Zoom, if you've watched this and you want to get a circuit kit, just let one of us know. But thank you so much for watching. We'll see you next week, and bye for now.
Are you gonna
You guys can start working.
Oh, yeah.